Hello everyone, welcome to lecture on formal verification using interactive theorem proving. My name is Dr. Vilayat Khan, and in this lecture I'll briefly introduce you to formal methods and in particular proof assistant COC, and I'll motivate why formal verification is more important as compared to conventional simulation and testing approaches. Formal methods or mathematical tools and techniques that are used to support the description of the software or hardware systems, its construction, and its formal analysis. Using any of the formal methods, a software or a hardware system is first described using the logic of formal method. Then the system is analyzed, or different properties, different reliability and security properties of the software system and the hardware system are proved to hold, and then the system is constructed. So mainly there are three aspects of formal methods: and specification, a formal model of the system under verification or the system of interest is created using the logic of the formal method. Then certain properties, reliability or security properties of the system are proved to hold, or in other words, it is verified that the model behaves as intended. It behaves or conforms to the specification of the system and fulfills certain requirements. When this analysis or formal analysis is complete about the system, then the system is constructed. If it is a software system, then an executable code is directly derived or exported from the specification of the system. Different formal tools allow users or designers to automatically extract executable code in different languages from the formal specification built in that language. So what is the impact of software errors on different systems and different users? The impact of software errors on different users is different. For a personal computer user, a software error is not that much significant. But for a car user, where the car consists of software codes, it runs on software codes. A number of software modules are used in the car to automate or to control the operation of the car or different components of the car. A software error in a car is more significant because the car can crash. So in general, in safety critical software, unreliability or bugs can lead to dramatic losses. For example, software errors in e-commerce, transportation, aviation, energy, telecommunication, defense can be catastrophic. In critical system, either human lives or huge money is involved. So a bug or software error in such system can cause millions or billions of US dollar loss, or it can also cause human lives. For example, a passenger plane have crashed can lead to human losses. So, safety of such system is more important than the safety of a personal computer. Then what is the challenge? The challenge or the problem is that software verification and testing is very expensive. It is not possible to test or verify a system for all possible cases or all possible scenarios. There are different companies that balance this verification process with facing losses. They don't verify or test their system and eventually they end up with losses. Then why should we care? Why is this formal methods, verification, testing, bugs, systems, critical systems, why is this all very important? Why should we care about them? Complex systems almost certainly contains bugs. And nowadays, most of the systems or many systems are very complicated. They consist of millions of lines of code, of software code. So it is easy to have bugs in such systems. And if the system is complicated, it is extremely difficult to identify bugs in the system. However, if a critical or complex system is critical, for example, it is used in the avionics, then it needs to satisfy or to meet very high standards of security and reliability. As a critical system involves human lives or can cause huge loss of money, it's important that the system meets certain high standards of security and reliability. However, it is infeasible in practice to achieve such high standards just by testing. Unfortunately, testing and simulation is widely used in industry nowadays, but just testing and simulation are not sufficient to meet such high standards that are required for the critical systems. Program testing or simulation can be used to show the presence of bugs. If there are bugs, some of the bugs can be found. Some of the bugs can be found. However, program testing can never show the absence of bugs in the system. If program testing can find 100 bugs in the system, this is not sufficient unless and until the verification technique ensures you that there is no more bug in the system. So this latter property, to show the absence of bugs in the system, is much stronger than finding the presence of some bugs. Program testing and simulation ensure the first property, it can show you the presence of some bugs, and the formal methods is useful to satisfy this latter property, to ensure you the absence of bugs in the system. To motivate formal verification and critical system, there are some examples of failures in the past. Ariane 5 crash. It was a European Space Agency project. It took 10 years of research and development. They spent around $7 billion on this project, and the rocket launched was exploded within a minute. This explosion caused the European Space Agency an estimated loss of around 370 million US dollars. When they investigated this crash, they found the system was trying to store a 64-bit floating point value into a 16-bit integer. This problem is called, or this bug is called, Overflow. Dirac-25. In 1987, this machine, Dirac-25, was used to diagnose breast cancer in the women. It selected value X for the X-ray instead of electrons for the beam type. Several cancer patients were killed and many were seriously injured due to UV radiation by this Dirac-25 machine. Another popular example was Intel FDIV Bug, the bug in the floating point division of the Intel machines. Intel used lookup tables to speed up floating point division calculation. However, a few entries in the table were missing. A professor of math noticed that there is a bug, and he proved that when this number is divided with this number, the correct calculation, the correct value of the division or of the result of the division is this one. But the Intel microprocessor that had the bug gave this result. So the digits in the red color are incorrect. Intel initially did not accept the significance of this bug, and they said that it was not serious because the probability of the error is very low. This error can happen in every 9 billion floating point division. This 9 billion figure is quite huge, but scientific programs, on the other hand, execute billions and trillions of floating point operations per second. So that means that the probability of this error is quite high. Intel had to replace those infected or buggy microprocessors, and it costed Intel 475 million US dollars. Quite recently, a bug at the Knight Capital Group costed Knight Capital Group around 440 million US dollar in just 45 minutes on stock exchange market. Knight Capital Group was a US firm that was engaged in electronic execution, sales, and trading. The company took 17 years to build, and it crashed in an hour. And the reason was that a critical flag was incorrectly used. So, what is the challenge? An intellectual challenge that we have. If we are designing a bridge, then the bridge must not collapse. That is the intellectual challenge in civil engineering. And mechanical engineering, the cars must be reliable. And if there is a software system in the car, it must be reliable. It should not fail. It should tolerate the faults. In terms of software power engineering, a smart grid controls different components, different departments, and it should be fault tolerant. Similarly, in software engineering, we must not see this screen. The softwares are safe. This is a challenge in software engineering. And when we are talking about software are everywhere. They are used in the cars, they are used in the airplane, they are everywhere. And to compare exhaustive testing and simulation, or to study its limitation, let me give you a simple example, a program code. This is the code written in C++. This is the main function that calls this function add, and it returns the sum of two integer values that have been passed as argument to this function. So the add function gets two integer values n and m. It returns the sum of these two arguments n and m. Now, using testing and simulation, if we want that this code or this function add must satisfy a simple property, commutative property, then we must ensure this for all possible inputs. The commutative property states that when the arguments of this function are swapped, the result will be the same. The result is not changed. If we want to prove this commutative property for this function add, we must try for all input combinations. For example, we can begin with add 3, 4, and then we swap. 4 is the first argument here and 3 is the second, and we can see the result. Of course, the result on left hand side and right hand side will be 7. We can try for this input combination. We can try another one, 1, 3 and 3, 1. Yes, the result are the same. Okay. We can try another one, 8, 2, 5, 8, 5, 2. Can we do this for billions of inputs? This is simply not possible in current resources, or it may be possible, but it will take many months or maybe many years, and the proof would then be not that much significant. In terms of hardware components, we can try exhaustive testing, but this is not possible for all possible input combination. In the example, we have a 32-bit adder, and this 32-bit adder hardware component gets two 32-bit values. A is a 32-bit value, B is a 32-bit value, and this adder adds the two 32-bit values and gives a 64-bit sum. For these 32-bit two values, the total possible inputs are 2 raised to power 32 multiplied by 2 raised to power 32 is equal to 2 raised to power 64 possible inputs. In the binary system, for a 32-bit value, we have 2 raised to power 32 possible values. But we have two values, another 2 raised to power 32 values, we have to multiply this, and the result is 64-bit sum. So in total we have 2 raised to power 64 possible input sets. If a super fast simulator is used, and assume this super fast simulator runs 2 raised to power 32 cycles per second. At this speed, this circuit will take around over 100 years to check for every possible inputs. Because the number of possible inputs is extremely large, it will take around 100 years. So formal verification and simulation, in terms of coverage of the design space, which one is better? Simulation can spot coverage of design space. Some possible cases or some possible input combination can be checked, can be verified, but simulation cannot verify the system for all possible input cases. As an example is the add function, where we saw that there can be billions of input combination. So we can just simulate or test the add function for certain inputs, but we cannot do this for all possible inputs. So assume this is the whole design space. The circle represents the whole design space, all possible input combinations, and we test the system for these limited number of input combinations. So it doesn't cover all the design space, and the answer and the reason is that it is simply not possible within the limited resources. On the other hand, formal verification in the ideal case provides full coverage of the design space. In ideal case, it can verify all the possible cases or all possible input combination of the system. But in practice, it provides full coverage, but in some areas it doesn't provide full coverage in all areas. Let's assume the circle represent all the modules of the system under verification. These colored boxes represent those modules which are of significance to the system reliability. So only certain or selected modules of the system are fully verified, and some modules which are not that much important or which doesn't play significant role in the system security or reliability, they are left out of the formal verification. And those modules or components which are significant to the system reliability, they are fully verified. So this is the practice in real life. Here we can compare formal versus informal verification. Here we have a pen and paper method. This is an absorption theorem of the Boolean algebra, and the example has been taken from the popular book Digital Logic Design by Maurice Manu. These variables are Boolean variables. They can take just two values, 0 and 1. And we have two Boolean operators. These two Boolean operators are symbols for two Boolean operations, logical OR, and there is an operator dot, which is for simplicity not used, that is logical AND. X plus xy is equal to x. This is an absorption theorem. And here we have a proof where x plus xy is equal to x dot 1 plus xy. And here we have some basic theorems which are used for the proof of this theorem, absorption theorem. And here we have a formal proof in Koch, which is a proof assistant developed by the INRIA Research Laboratory in France. This is a machine readable proof here. This is the proof that can be read by a machine, a computer machine. And here we have a proof that is called pen and paper method proof or informal proof. To proceed with pen and paper proof, we can take on the left hand side of the theorem x plus xy, which is equal to x dot 1 plus xy. This x is replaced with x dot 1 because we have theorem here, theorem 4, x dot 1 is equal to x. This list is the list of some postulates, 6 postulates and some theorems. Each one is numbered, and postulates or axioms that do not require proof, but theorems require proof with the help of axioms or postulates. For simplicity, I will just refer to each of these postulate and theorems as theorem, and the number in the parameters is the number of that theorem. So theorem 4 is used, x dot 1 is equal to x. So x is replaced with x dot 1. Then this x dot 1 plus xy is replaced with x dot 1 plus y, and the theorem that is used is distributive property here. And then 1 plus y is replaced with 1 in this pen and paper proof method. But we do not have a theorem or postulate like 1 plus y is equal to 1. We have a theorem x plus 1 is equal to 1, but there is no proof theorem 1 plus x is equal to 1. So this step is missing here. For the time being, we just continue. And this 1 plus y has been replaced with 1, even though there should be an additional step which I will highlight here in the formal proof. So 1 plus y is replaced with 1, so we get x dot 1 here, and this x dot 1 is then replaced with x because we have a theorem for this, and we complete the proof. On the contrary, we have a formal proof in Koch theorem prover. Initially, to have a lemma of this kind, the Boolean algebra has been formalized in Koch theorem prover, a formal model of the Boolean algebra, the Boolean type, the two operators. All this is defined, and then we can state theorems or lemma just like this. So we can give a name to the theorem that we want to prove, and that is absorption sum. This is the keyword, and then we used for all x, y, which are the two Boolean variables, and the type bool is not mentioned here because Koch theorem prover can predict the type of these two variables from the definition of the logical OR and the logical AND operation. So x plus xy is equal to x. Then the proof of this theorem or lemma begins with the proof command, which is called tactic. Koch understand that the proof has just begun. I will skip these two tactics. Here we have 4 tactics that refer to the 4 postulates or 4 theorems of the Boolean algebra. Just to compare this formal proof with the informal one, at this stage we apply the identity product. This is the theorem, and the name here in the Koch proof for this theorem is identity product. So identity product is written here or applied here using the rewrite tactic. Then this whole term is replaced with this one by using distributive property over sum. Here is the distributive property over sum, and it is the name distributed over sum in the Koch proof. Then 1 plus y was replaced with 1 in the pen and paper method, a step was skipped, and the same step is included here. 1 plus y is first replaced with y plus 1 because that is what the commutative property says. We apply the commutative sum property. This is the commutative sum property, and we derive this term from this one by applying commutative property. This is the missing step and this informal proof method. Koch theorem prover will not allow to apply this next theorem after this one. This Koch will not allow, and this is what we need. We should follow the correct path of proof. We should not miss any step. After commutative sum theorem, we apply identity sum, and the rest of the proof is similar to the pen and paper method proof. 1 plus y is replaced with y plus 1, and then y plus 1 is replaced with 1 because that is what x plus 1 is equal to 1, so y plus 1 is also equal to 1, so we get x dot 1. And finally, we apply identity product theorem, which is here, identity product, and we get x dot 1 is equal to x, which is the end of the proof. So, how formal verification and verification, formal specification and verification proceeds. If we have a system, hardware or software system, that we want to verify, by verification, we are interested that this system must satisfy or fulfill these requirements. After formalization, one can build or create or define a model of this system. This is the system, hardware or software system. A model is created. A formal model is created. These requirements are also stated or defined or modeled, which is then called specification. Then this model and the specification are provided to the verification tool. This verification tool will then verify if the model of the system conforms to the specification, or in other words, this verification tool will verify if the model satisfies these properties or not, and it will give the result. The result will be either yes, the model satisfies the requirements or the model conforms to the specification, or it can be that the model does not specify the requirements, and will provide a counterexample for that. To map this flowchart to our example program aid, our system is program 8 in this example, and that system is a software system. The requirements that we want to satisfy for this system is the simple commutative property. After formalization, a formal model of this program 8 is created. This can be simple as this function. And similarly, the requirement, which is the commutative property in this example, is formalized like this. This formalization of the model and the requirements depend on the logic used in the formal method. Then both this formal model and the specification are provided to the verification tool, which is called theorem prover. This theorem prover then proves if the model conforms to this specification or not. The theorem prover tools, the computer-based theorem prover tools are classified as automated provers or interactive provers. The major difference between these two categories is that automated theorem provers automatically proves or disproves the system or the theorems without the help of or limited help of or with the limited help, without the user help or with limited user help, while interactive theorem provers require the assistance of a proof engineer. The main focus of this course is interactive theorem prover, and in particular a theorem prover called Coq theorem prover is introduced. Automated reasoning is what we need, is what we want, but this is still a dream because automated reasoning suffers from a number of problems like state explosion problem, where a system, a computer system, gets some exams and proves these theorems without the help of user. Such automated reasoning tool may get into an infinite loop and will not return. When such a tool does not return, one cannot be sure if the theorems have been verified or not. There are interactive tools as well, which is called interactive reasoning. This is the practice. In interactive reasoning, an interactive tool gets a set of exams, and this tool, with the help of this user, which is normally a proof engineer, can prove the theorems. In interactive reasoning, the interactive tools doesn't face issues like state explosion problem where the system gets into an infinite loop. This proof engineer provides proof command to this tool or the system. Those proof commands are called tactics, and the interactive tools are normally called proof assistant. And a proof assistant that we have chosen for this course is Coq theorem prover. Further detail about interactive theorem proving and Coq proof assistant will be given in coming lectures. Thank you.